Hello, everyone. My name's Michael Neal, and I wish you a good whatever time of day it is that you're looking at this presentation. I'm here to teach you a little bit about statistical methods that are particularly useful in genetic studies. And of course, geneticists, like many other fields of study, are very interested in variation. In fact, you can call variation the stuff of life genuinely, because without it, there is no evolution. And without evolution, there would be no us. So when we think about statistics and the way individuals vary from each other in the population, typically it begins with measuring a lot of people in the population, and for many traits that are caused by a very large number of factors, each having a very small effect, we end up in the population with a bell curve, that is a normal distribution type shape. This is really just an expansion of the binomial theorem for very, very many independent events, each of which having a small effect. So our distribution in the population of the traits may look like this, but regardless of the shape of the distribution, we can still calculate three main statistics. The mean, which is simply the sum of the scores of everybody in the sample divided by the number of people in the sample. The variance, which you may think is a considerably more complicated thing, is actually still pretty simple, because once you've calculated that mean of your x, your distribution of the variable x, all you have to do is subtract the observations, each observation from that mean, square that deviation. So it's the square of this quantity over here, the deviation from the mean, and again, take the average, divide it by the number of observations in the sample. Finally, in the case that you have two variables, what you do is take a cross product where you take the difference of the first variable from its mean and multiply that by the difference between the second variable and its mean, and again, divide by the number of observations in the sample. So these are basically per person types of measures of what the average score is, what the variation is, and what the covariation is in your sample. So how do we use these statistics? Well, they can actually help us with answering questions about what is causing what. And that is really a very fundamental thing in science, is that we want to analyze causes. And structural equation modeling was also used to be known as causal analysis, enables the specification of particular hypotheses about causation and enables the rejection of some of those hypotheses. So if we adopt the Popperian viewpoint of science, that kind of the best thing that can happen to a hypothesis is that it is not rejected, the ability to reject hypotheses is kind of key. So structural equation models began in around 1921, i.e. 100 years ago, when Sewall Wright developed a number of the principles for what we call today structural equation modeling, or SEM for short. And SEM consists of two types of relationships between variables in the diagram. And the two types of relationship primarily are the causal pathway, X causes Y, as we see over here. And also the alternative is to put an unspecified covariance. So we're saying we know these things covary for some reason. We're not really sure what it is, so we're not going to put any variables up here to account for it. But we just assume that there are sources of covariance, common causes of the covariance between X and Y. Structural equation models primarily deal with two types of variables. That is, the observed variables drawn in boxes and a latent variable which has not been directly observed, drawn in a circle. There are a couple of other types of embellishments to path diagrams, particularly adding triangles for specifying models for the means, which turns out to be useful in areas such as growth curve modeling, where we're trying to predict not just the change in mean over time, but also change in covariance structure or variation over time. But we'll stick just with the two main types of variable. Now, the utility of path diagrams, and here's a path diagram for a simple common factor model. The utility is that it enables us to write down equations for the variances and the covariances between the observed variables in our study. So in this particular case, there are three observed variables, V1, V2, and V3, and there's a latent factor, F, which is thought to partly cause each of the observed variables. And the degree of causation coming from this latent factor is estimated by a regression coefficient, in this case, lambda 1 for the regression of V1 on the factor, lambda 2 for the regression of V2 on the factor, and so on. In addition to that variance due to the factor, these observed measures will have some variation specific to them. And we draw that as a double-headed arrow, i.e. a covariance of the variable with itself, and write the path coefficient next to it. At the top of the diagram, we have a latent variable, the factor. Now, because the factor isn't directly measured, we can only know one thing about it. That is, we can't know its variance and its causal effect, because you could have more variance and less causal effect and get exactly the same fit. So we can't actually estimate the variance of this latent factor if we estimate all of these factor loadings as well. And so one common solution to this under identification problem is to just fix the scale of the latent factor to 1. And that's very broadly used in genetic studies, including studies of twins. But note here that it's often the latent factor that we're interested in. We can't necessarily measure somebody's intrinsic depression just by looking inside their head and saying, oh yeah, it's this far up on the thermometer of the depression scale, or we can't stick something in their ear to measure depression. It doesn't manifest itself as a trait like that. But it does manifest itself as a series of signs and symptoms that we might be able to inquire about, like whether the person's had a period of 2 weeks or more where they felt really down and depressed and maybe crying a lot of the time. You know, if they've experienced suicidal thoughts, or sleeping too much or sleeping too little, various different disruptions to the system. And we could measure those individual symptoms and derive ourselves something of a factor score for just how depressed that person is. And that's part of the function of a factor model. And the factor model is just one example of a type of structural equation model that involves both latent variables and observed variables. Okay. So the two kind of cool things about structural equation modeling is there's a couple of ways to derive all the expected covariances between the variables in the diagram. And one is through a set of tracing rules with which you can calculate any particular variance of an observed variable or covariances between different variables. And simply by following these rules, one can derive those expectations by hand. Of course, in a large structural equation model, one doesn't particularly want to calculate lots and lots of different covariances with potentially many terms in them by hand, because this will increase the chance of an error between initially specifying the model and when it comes time to fit it. So there are better ways generally of specifying models that are less likely to involve typographical or calculation mistakes along the way. So there's a matrix approach, which is completely general, and it's really nice and really simple. So we can give this a go. So these are the so-called RAM algebra. These are due to McArdle and MacDonald, two highly esteemed quantitative psychologists, friends of mine. And the general approach for the RAM algebra is to arrange all of the path coefficients, that is the regression paths and the covariance paths, into one matrix each, and then calculate the expected covariance matrix of all of the observed variables, which is what we're going to use to fit the model. So this organization is really just done in two matrices, one that will contain all the double-headed arrows and one that will contain all the single-headed arrows. And we then use the formula at the bottom of this slide to compute the expected covariance matrix. And let's have a walk through the factor model that I just showed to see how this works. So first of all, we're going to organize all the latent variables and all the observed variables into a single vector list. So we've got the variables f, v1, v2, and v3, and these become the labels for the rows and the columns of the symmetric matrix S, where the double-headed arrows, the slings. McArdle used to refer to the slings and arrows of outrageous fortune in referring to the S and the A matrices, for slings for the double-headed and arrows for the single-headed. So the matrix S, the variance of F, that is, there is a double-headed arrow from F to itself, and this is given the value 1. And so that enters on the leading diagonal of this S matrix. The covariance between F and F is simply 1. The other residual covariances at the bottom similarly enter on the leading diagonal, with psi1, psi2, and psi3 being the residual variances specific for the v1, v2, and v3 measures. So that deals with the double-headed arrows in this figure. The single-headed arrows in this figure are also arranged in a matrix with exactly the same number of rows and columns. But these, in this case, are organized. Because this is an asymmetric matrix, the from and the to could be quite different. If there was another arrow going from V1 back to F, that would appear instead of a 0 in the V1 to F element of this matrix. But you can just see that the only single-headed arrows in the simple factor model are going from the factor to the variables v1, v2, and v3. And I've gone forward a slide and I'm going to go back one. And so the quantities, the parameters to be estimated, lambda1, lambda2, and lambda3, all appear in this first column of the asymmetric A matrix. So then moving on, this eventually would give us the covariance of all the variables in the diagram, but we actually want to reduce it to only the observed variables, because those are the things that that's the set of variances and covariances that we want to fit to our observed variances and covariances from conducting a multivariate study measuring several variables on individuals and estimating those covariances and fitting a model to them. In practice, we do it slightly differently, as I'll explain shortly. So finally, the filter matrix, all the filter matrix does is get rid of the latent variables from the rows. So we're just going in matrix F, we're going from all the variables to the observed variables, and it's only when the labels of the row and column are the same that this matrix gets an element of 1. Otherwise, its value is set to 0. So, having organized those three matrices, we can use the RAM algebra formula. And so this is F multiplied by the identity matrix. That's just a matrix with 1s down the diagonal and 0s everywhere else. Take this quantity and invert it, and then compute what we call a matrix quadratic. So that's a matrix times another matrix times the first matrix transposed. And this quadratic product would give us the covariance between all the variables in the diagram, and the quadratic for F simply reduces the rows and columns to only the observed variables. And it's at this point that we can inspect the expected variances and covariances in this matrix that we've calculated. And it turns out that these miraculously, well, not so miraculously, because the diagram is mathematically complete, and by and large, coincidences don't really happen in mathematics. It is beyond coincidence that this is the same as we get out of applying the rules. But for example, the covariance between V1 and V2 by following the tracing rules will be going backwards along 0 or more arrowheads. So we can go lambda1, change direction up here and multiply that by 1, and head back down an arrow, lambda2, to give us lambda1 multiplied by 1 multiplied by lambda2, or just lambda1 lambda2, for the expected covariance between variable 1 and variable 2. And this expected covariance matrix is, of course, symmetric, because we expect the covariance between variable 1 and variable 3 to be the same as the covariance between variable 3 and variable 1, for example. But in following through this list, I mean, the one other trick to notice here is calculating the variance of V1. Again, that's retreating along 0 or more arrowheads, changing direction at a double-headed arrow, and proceeding forwards through the arrow again. And that gives us lambda1 times 1 times lambda1 is lambda1 squared. But there's another path chain here, that is the residual component of variance. And again, we're going to go backwards through 0 arrowheads, just change direction here at psi1, and proceed forwards through 0 arrowheads. So it's still a legitimate chain, even though it hasn't actually got any of the directional arrows in it. So overall expectation for the variance of V1 is lambda1 squared plus psi1. So different chains get summed in structural equation modeling. Okay. There's also a formula for the means, and there are ways to calculate the means, but as I say, we won't be making much use of that during this course. So just to note that it's there, and it has a similar kind of half of the expectation for the covariance algebra in order to calculate it. So that brings us to needing some software to fit such models to the data. And it was a ridiculously long time ago that I started developing some software that I called MX, kind of a short for matrix, as the software had something like a calculator that would take parentheses and other types of operations, but it was a calculator designed to deal with matrix algebra. So you could take the RAM formula or any other matrix formula you happen to have your hands on and want to model with, and let different elements of those matrices be free parameters, and then tie that up to a numerical optimizer to say, okay, optimizer, those are your free parameters, fiddle around with them as much as you like until you get the best fit of the model to the data. So we'll change the parameter values and try and get the predicted variances and covariances to be like a really good match for the observed variances, covariances. OpenMX was the successor to my standalone MX software. We began developing it a bit over 12 years ago. It's an established R package on CRAN, which means that it is necessarily an open source package. We have different ways that users can specify models. You can specify them in matrices, as I just described, but you can also provide path style input. And there's ancillary software such as Onyx, which can generate OpenMX scripts directly from diagrams that you draw. OpenMX is a very fully featured structural equation modeling program and contains a large number of extensions, some of which you can find in other packages and others you cannot. It has the usual kinds of fit functions for structural equation modeling, and was particularly innovative in the development of full information maximum likelihood, which is particularly useful for dealing with data sets where you have missing data. And I don't know about you, but any reasonable sized data set that I've come across always has missing data. If somebody tells you they don't have missing data, just step away, step away. What can we do with OpenMX in this case? As I mentioned that Onyx is a Java path diagram drawing program. There are other open source packages for doing structural equation modeling. These include SEM and Lavaan. These are perfectly decent packages. They don't have as extensive a feature set as OpenMX, but they're still fit for purpose. And I think you will probably see some Lavaan syntax when it comes to genomic SEM later in the course. There are, of course, other offerings for structural equation modeling, things like LISRUL, M+, and AMOS, and perhaps a few others. These are commercial packages, meaning you've got to pay money to use them. And because they're closed source, they're not really fit for reproducible science. If you can't actually see the code and see how it does what it does, you should probably suspend your trust in the software until you've made sure with every single model that you fit that you can recover the parameter estimate. So you get a kind of Turing test of putting questions into this black box of software. And as long as those answers come back looking reasonable, you conclude, okay, it looks like it's doing what I want it to do. That is a very different level of evidence that it is doing what it's supposed to do from entering the room and seeing if there's really a human behind the door, or similarly entering into the source code and seeing if the source code calculates things the way that it is supposed to. And so I'm a very strong proponent of open source software and consider it to be like publishing articles. There are no secrets in open source software. By it being open source, it enables people to improve it. That's consistent with basic scientific principles. That is, we're making contributions to the scientific literature, and open source software makes contributions to the scientific technologies that we use for science in general. Okay, I'm going to stop there.